Okay, so now we'll begin to look at some important properties of the integers, and we will start with a set of axioms for the positive integers, and these axioms together are collectively known as the Peano axioms. Now remember, an axiom is a statement that we accept as a fundamental fact without proof. The first is that the number 1 is in the set of positive integers, or natural numbers. The second is that if a given positive integer n is in the set of positive integers, then its successor which is the integer n plus 1 is also in the set of positive integers. If m and n have the same successor, then m and n are the same positive integer. The number 1 has no successor. And finally, if a subset, a non-empty subset, A of the set of positive integers contains the number 1, and if it contains n plus 1 whenever it contains the integer n, the positive integer n, then that subset is necessarily equal to the entire set of positive integers. Alright, so these axioms, I don't believe that anyone will really argue with them. They're pretty straightforward, and it's easy to accept them as fundamental facts. But let's go over them. The number 1 is, of course, in the set of positive integers. And because the positive integers are countable, they can be listed in their proper order. So if a given integer n is in the set of positive integers, then n plus 1, its successor, is in the set of positive integers. The third axiom, if m and n have the same successor, then they must be equal, and that's pretty clear. The successor of m is m plus 1, and the successor of n is n plus 1, so if they have the same successor, these two are equal. And so, of course, m is equal to n. The fourth statement, 1 has no successor. This is another way to say that 1 is the least element in the set of positive integers. In other words, the set of positive integers begins with 1. There is no number smaller than 1 that starts the set of positive integers. And the fifth statement, any non-empty subset of the set of positive integers that contains 1 and which has the successor for every other element, or for every element, must be equal to the entire set of positive integers. Now, these axioms together have two very important consequences that we will use quite often. The first is that the technique of proof, known as proof by mathematical induction, is really a restatement of these axioms. Remember that in mathematical induction, we start with a basis step. We, in other words, show that a set of premises is true for the case n equals 1, that is, a piece of 1 is true. And then if we can show, using the induction step, that if we assume that piece of k is true, and this implies p of k plus 1 is true, then in essence we're saying we have a set an infinite set of premises, which is true in the case n equals 1, and it's true, the case p piece of k plus 1 is true anytime that piece of k is true. We're in essence showing that the entire set of premises is true for the set of positive integers. And so, again, the Peano axioms can be restated in the form of what we know as proof by mathematical induction, and they are equivalent. And so that is why the proof technique known as proof by mathematical induction is valid. Another consequence of the Peano axioms is that is what we know as the well-ordering principle for the set of positive integers. So let's state that. And this is as a theorem, the well-ordering principle of the integers. And this can be stated: any non-empty subset for any non-empty subset A of the set of positive integers, there exists an element M in the set of positive integers, actually in the set A, subset A, such that M is less than or equal to A for every element A in the set A. And we call this element M the least or minimal element of the set A. Now, to be completely accurate, we should say that the element M is the least or minimal element in the poset where the order is the less than or equal order. And of course, we can write that the minimum of this poset is this element M. All right. Now, I stated this as a theorem, but no real proof is required, as this is a direct consequence of the Peano axioms. But we'll go ahead and walk through or talk through an outline of any proof if you feel you need one. First of all, any subset of the positive integers may or may not contain the positive integer 1. If it does contain the positive integer 1, then 1 is the least element. And that comes from, again, directly from the Peano axioms. Now, if that subset does not contain the number 1, then it again must be a non-empty subset, so it contains at least one element. If it is a singleton set, then that single element is, of course, the least element. If not, it is larger than a singleton set, and one of those elements, it will be true that it is smaller than all the others, and that will be the least element. So for any non-empty subset of the positive integers, there exists at least one element, and I'll clarify what I mean by at least in a moment, at least one element in that set, such that for every other element in that set, that element is less than or equal to it. Now, when we use orders that are not necessarily the less than or equal to order, we will see that we must make a distinction between a least element and a minimal element. And so I'll hold off on that until we arrive at that. All right? So now a new definition. Let the set A with some relation R be a poset, or a simply ordered set, such that the relation R is a total ordering on set A if every non-empty subset of the set A has a least element then this totally ordered set or simply ordered set is called a well-ordered set. Okay, so we'll look at an example. Notice that both the totally ordered set consisting of the set of integers together with the relation less than or equal to, and the simply ordered set consisting of the integers and the relation strictly less than, neither are well-ordered sets. And this is true since the set of negative integers is a subset, in fact a proper subset of the set of integers, and this subset has no least element. Now, in the definition for a well-ordered set, there's two things that have to be true, in particular when we're talking about a post set. The order relation must be a total ordering, and that is true for this post set. The relation less than or equal to is a total ordering on the set of integers. And the other thing that must be true is that any subset of the given set in the post set must have a least element. And that is not true of the set of integers, as the set of negative integers is a proper subset that has no least element. So we'll show that the post set consisting of the positive integers with the relation less than or equal to, and the simply ordered set consisting of the positive integers with the relation strictly less than, both of these are well-ordered sets. Now, we already know that the set of positive integers with the relation less than or equal to is a totally ordered set, and the set of positive integers with the relation strictly less than is a simply ordered set. And so the only thing that we need to demonstrate is that the any positive, or rather any non-empty subset of the positive integers is or does contain a least element. And to do that, we simply go back up to our theorem, and by this theorem we know that every non-empty subset of the set of positive integers has a least element. And so really not much to show here. Both the post set, the totally ordered set consisting of the set of integers together with positive integers together with the relation less than or equal to, and the simply ordered set consisting of the positive integers and the relation strictly less than, are well-ordered sets. Okay, so now a new definition, and we start to look at topics that are traditionally found in a number theory course. Let A and B be two integers. Then we say that A divides the number B, or the integer B, if there exists an integer C such that B is equal to A times that integer C. So in other words, a given integer A divides a second integer b if that integer a is some integer multiple, or rather that integer b is some integer multiple of the integer a. So there's a few things we can see immediately from this definition. The first is that 1 divides any integer a. And this is true since a can be expressed as a multiple of 1. In fact, a times 1. Another thing that is immediately obvious from this definition is that the integer a divides itself. And this is true, again, for any integer. And we can show this as a is a multiple of a, namely multiple of 1. Another thing is that the number 0 does not divide any integer. There does not exist an integer n such that any integer a is equal to n times 0. And so the number 0 does not divide any integer a. However, the number 0 is divisible by, or any integer divides, the number 0. So for every integer a, we have a divides 0, since 0 is equal to a times 0 for every integer a. All right. So now we're ready for a theorem. Let a, b, d, r, and s be integers such that d is not equal to 0 if d divides a and d divides b, then d divides any linear combination of a and b, in particular ar plus bs. Okay, so suppose that d divides a and d divides b. Then, by definition, a is some integer multiple of d, so we have d times e, and b is some integer multiple of d, and so we have d times f for some integers e and f. And so AR plus BS is DER plus DFS. And so if we take out the D, we're left with ER plus FS. That is, the linear combination AR plus BS is an integer multiple of the integer D. And so we have that the integer D divides this linear combination, AR plus BS. So a very useful theorem. If we have an integer that divides two other integers, then that integer D divides any linear combination of the two integers that it divides. All right. So now a new theorem. In this one, we'll establish the transitivity of the relation divides. Let A, B, and C be integers such that A is not 0 and B is not 0 if A divides B and B divides C, then A divides C. Okay, so suppose that A divides B and B divides C. Then, by definition, B is equal to some integer multiple of A, and C is equal to some integer multiple of B. And so we have that C is equal to the integer B times F, but that is B is itself a multiple of A. So the integer C is some integer multiple of A, and so A divides C. Okay, new theorem. Let A, B, and K be integers such that K is not 0. Then A divides B if and only if A times K divides B times K. Okay, so first suppose that A divides B. Then B is some integer multiple of A. And so B times K is AE times K, which is A times KE, which is AK times E. So BK is some integer multiple of AK, and so A times K divides B times K. All right? So conversely, suppose that A times K divides B times K, then B times K is some integer multiple of A times K, sum E, in a set of integers. Now, as the integer K is not 0, we have that B is equal to A times E. That is, A is some integer multiple of B. And so A divides B.